Okay, we're going to talk about electronegativity trends on the periodic table. First, of course, we're going to define electronegativity, but after we do that, we're mainly going to be talking about what happens to the characteristic of electronegativity in atoms as you go from left to right on the periodic table and from bottom to top. So here we go. So first off, electronegativity is an atom's ability to attract electrons when it's part of a chemical bond. And that ends up being incredibly important in a lot of different areas of chemistry, even as something as simple as a water molecule. You can see here the oxygen atom, which is a lot more electronegative than the hydrogen atoms, pulls electrons away from the hydrogen atoms, where the electrons spend more time on the oxygen side, to the point where it develops a slight negative charge here. The hydrogen side will develop a slight positive charge. Now, this is a little bit of a preview of some stuff that we're going to do to come, but I did want to illustrate why electronegativity is important. And again, the main property is basically just the ability to attract electrons. That's how it's said formally. More informally, it's the degree to which an atom is an electron hog. That's how I will say it pretty much every year that I teach it. So how greedy it is for electrons. You know, one thing I wanted to mention on this that's very important for pretty much any student is that being able to understand electronegativity is just absolutely critical for a number of topics that'll come up later in any sort of general chemistry course. And if you don't understand it, you won't have a prayer of understanding the stuff that's to come. So make sure you're paying attention. As it says down here on the bottom, it's not super hard, but if you get lost, you tend to stay lost. It's like an algebra. So please take advantage of the fact that it's not really hard. Just, buckle down and focus a little bit, and then you'll be all set up for the stuff that's to follow. All right, so for an analogy here, I typically use this analogy when I'm teaching this about trends, having to do with trends. If you understand the trends in temperature on any typical weather map, then you should understand trends in electronegativity. And so starting out talking about something like this, like for example, if we were to talk about the temperature in Moose Knuckle, Alaska, or the temperature in Bangor, Maine, or say Washington, D.C., or Franklinton, Louisiana, or say Miami, Florida, if we were to try to figure out which of these temperatures go with which place on the map, we could start out pretty easy with this, because we naturally assume that the very coldest temperature, for example, would end up being in Moose Knuckle, Alaska, and it almost certainly is. The very hottest temperature would be in Miami, Florida, and then all we'd have to do would be to fill in the rest. The second coldest temperature is almost certainly going to be in Bangor, Maine, then followed by Washington, D.C., and then finally Franklinton, Louisiana. So in talking about this, we also want to consider that every single spot on this map does not necessarily correlate. The temperature doesn't necessarily correlate with how far north or south it is. For example, here with Arizona, New Mexico, Texas, you've got some areas here that are warmer than some places in Louisiana, Mississippi, Florida, even though they're further north. The rule is supposed to be the further north you go, the colder you get. Well, it's not always a one-to-one relationship with how far north you are versus how cold it is. But the overall trend is the further north you go, the chillier it gets. And that's what we work with, and that's what works most of the time when we're talking about trends on the periodic table. So, speaking of which, here's our periodic table. And the good news here is we're going to be able to pretty much ignore about a third of this table, because about a third of this table, in fact, doesn't quite fit in with our trends, but would make some very useful predictions on the areas it does. For example, on the bottom, on the intertransition metals, basically, they've got a pretty complicated chemistry, so they don't really fit into the sort of trends that we're talking about. Also, the transition metals right here, they've got a pretty constant electronegativity, it turns out, across here. So those actually don't fit in. But if we just kind of cram these together, then we can make a decent little presentation on how electronegativity trends work. One last thing on this is that the noble gases, they have a full valence shell. They don't want electrons. They don't attract electrons. They don't form bonds. And so they're typically not taken into consideration in any of the discussions of electronegativity. But I found I need to leave these in when I teach this, because oftentimes if I take them out, people will get the group 7 and group 8 mixed up, and they'll end up thinking that they'll end up answering on a test something about, the noble gases having something to do with electronegativity, and they're typically not considered in electronegativity trends. Anyways, just to kind of, I keep them in there just to sort of keep our bearings. Anyway, the main thing to consider is that electronegativity increases from the left to right across a period. So as you go this way, atoms get more and more electronegative. They tend to get more and more electronegative. And it's for a very simple reason. It's because the number of protons increases, so you got an increase in the effective nuclear charge, and so that tends to attract electrons. Now, you also gain electrons as you go from left to right, but those are all in the same energy level, which turns out not to have as much of an effect on electronegativity. Also, electronegativity increases from bottom to top within a group. So as you go from down here on the very bottom up to here, also you get an increase in electronegativity. And that's mainly because there are fewer energy levels around the nucleus. That is, less shielding, something called shielding. Whereas out here on the elements that have 7 energy levels, you've got all these different other intervening energy levels between the outer electrons and the nucleus. So not only do you have the attraction of the electrons to the nucleus, but you've also got repulsion from the electrons in the other energy levels. So that lessens the attractions of both the electrons in the valence shells and also any electrons from any other atoms that you might have that might be attracted to that given atom. So if you follow these patterns, the trends predict that fluorine is going to be the most electronegative element, and it is. Fluorine is the biggest electron hog, and I usually will suggest to students to make sure to memorize that. Number one, because it is typically a test question in any standardized test. And then number two, it'll also help you remember these trends of left to right and bottom to top. You run right into fluorine when you follow that sort of pattern. And also, just incidentally, cesium is the least electronegative element, depending slightly sometimes on how the electronegativity is calculated. It's typically referred to as cesium. And it's also a really good example of how it's not always one-to-one relationship, just like in that weather map that I showed a minute ago. So anyway, these are the basics of electronegativity, so that you'd be able to answer questions. For example, if you were to be asked, which is more electronegative, carbon or oxygen, and just from this pattern, you'd be able to take a pretty good guess that it was going to be oxygen. Or if you said, for example, which was more electronegative, polonium or sulfur, you would have a pretty good guess that it would be sulfur. So these are just basically rules of thumb that you can go by if you don't have the actual electronegativity numbers, and they're used fairly often for a lot of things, including things like what type of bond is formed, whether a molecule or a compound is formed, what type of melting point a compound might have, and all sorts of other important things like that. So that is it on the introduction to electronegativity, and later on we're going to present things like atomic radius and ionization energy, but that's it for now.